Good. So we're going to start to move on to a new topic, which is SPARQL, the query language for RDF. So last time we spoke a lot about RDFS. We had one class on RDFS and 3 classes on OWL. We're going to move on to, okay, we were speaking about the part of logic, about how to define these sorts of entailments that we might like to have in our data. So we're going to move on in today and in the next class next week to talk about the querying on the semantic web. So how do we express queries over RDF data? So the answer to that in short is SPARQL. So there's 2 versions of SPARQL, SPARQL 1.0 and SPARQL 1.1. So in this class, we're going to focus on the original version, which was extended for SPARQL 1.1. So first SPARQL 1.0 and then SPARQL 1.1. So here we have some example data that we've seen before, which relates to the Sharknado series, my favorite series of movies. Where we see Sharknado series as first movie, second movie, some of the people who star in these movies, the dates or the date of this movie, the name of this movie, the names of the movies. And now we wish to ask who stars in Sharknado. Okay, so who stars in Sharknado? So here's the movie Sharknado, and we see that we would expect John Hurd and Inzering here to be answers. So how do we write this sort of query down? Here is a simple example of a SPARQL query, which looks a little bit like SQL. So we have, first of all, a mix between SQL and Turtle somehow. So we start off with some prefixes, which are similar to what we define in Turtle, which allow us to make shortcuts of full IRIs. And then we have a select, like in SQL, star, which means return all of the variables. And then we have a where clause. And in the where clause, we can put effectively Turtle. We can put Turtle data with one important change, which is that we can put variables in there. So a variable, we start with a question mark. So what this asks for intuitively is give me all of the things that are the objects of triples where the subject is Sharknado and the predicate is stars. And if we look at the RDF graph here, we see that, okay, it would match this triple here, Sharknado stars, question mark would be John Hurd, and Sharknado stars Inzering. So we would match Inzering and we would get these solutions here, mapping essentially the variable to the elements of the data, right? So what does this mean? It means that if we take every solution, okay, John Hurd is one solution, and we replace the variable here with that solution, John Hurd, then the result is contained in the graph, right? So Sharknado stars John Hurd is contained in the graph here, right? And we get a solution for each such mapping of variables to terms in the RDF graph. So we're going to talk about this in more detail, what we can express in these queries and so forth. Any questions or doubts? We're good? Okay. All good. Cheers. So, okay, prefix declarations, not much to say. Okay, so we can define prefixes that are, it's pretty much, the syntax is slightly different to Turtle. I think Turtle ends with a period or full stop, but it's essentially the same idea as Turtle, which is that we can define some shortcuts that we can use here to avoid having to write full IRIs in our query. That's the prefixes. Okay, so the where clause is probably the most important part of the query. So it specifies what to match in the data. So here we see our where clause. So what we call here, this here is a triple pattern. So much like we have triples, we also have triple patterns. And triple patterns are just triples where we can have variables. We can replace any term we want with the variable. And that's intended to say match this element of the triple in the data. So Here's our query again that we already saw, looking for stars of Sharknado. And we see one match here, and we see another match here. Okay, so we get a solution for every such match. And we return the solutions that we saw before. So this is a simple workflow. What if we wanted to ask what movies did the stars of Sharknado also star in? So for example, we have Inzering is a star of Sharknado, but he also starred in Sharknado 2. So we'd like Sharknado 2 to be a solution for our query here. So how do we do this? This time we see that somehow the pattern we want to match involves two triples, right? Or two triple patterns, because first of all, we have to make sure that it's a star of the Sharknado movie. And then we have to use another triple to find what else they might have starred in. So it's sort of like a join. So how do we express this query? Well, we kind of like, we write it as if it were RDF, right? We say Sharknado stars, and then, okay, here we write a variable. Okay, so Sharknado stars, some variable star, movie stars, some variable star, and then we're looking for solutions for that. Okay, so what does this match? So we have Sharknado stars Inzering, and Sharknado 2 stars Inzering. So we could expect Sharknado 2 here and Inzering here. Are there any other solutions possible? In fact, there are two other solutions that we could have. Anyone want to guess? So we're going to have three solutions in total. So one is Inzering and Sharknado 2. Another would be to map movie back to Sharknado again, right? So we see if we replace star with Inzering and movie here with Sharknado, that we get Sharknado stars Inzering, Sharknado stars Inzering, and that's essentially a duplicate triple, but both of the triples are that one triple is contained in the RDF graph, so it's also a solution. So we also get a solution for John Hurd in the same way. So if we map movie to Sharknado again, and we move start to John Hurd, we see that everything fits in the graph, right? And the last one is Inzering stars Sharknado. So we get these results here. Inzering Sharknado 2, Inzering Sharknado, John Hurd Sharknado. It's worth mentioning that this refers to homomorphisms in graphs. So a homomorphism, there's a homomorphism and an isomorphism. A homomorphism allows you to map multiple nodes of one graph to another. And isomorphism, you have to map each node one-to-one. So, or subgraph isomorphism, where you map it to a subgraph of the other graph, but you map every node in a one-to-one manner to that subgraph. So what's the point here? The point is that we can map multiple variables to the same thing, and that's fine. And that allows us here to get three answers. So, okay.
Teacher?
Yep.
Yeah, on the first one, when you define star, it returns the actors. But on the next one, you use again the interrogation mark at star at the end. So because we defined it before, that's why we now get the movie one.
Yep, it's like in this here, the star here, we can use it multiple times, but it always has to be replaced by the same term in a solution, right? So what this, it's like a join between star here and star here. And then, yeah.
No, I was going to ask that since we defined star before on the first line, that's why on the second line it's used as a variable, because it's already, you know, defined. We know that the stars of Sharknado are Ian Searing and John Hurt. So now we look for the movies of those people.
Yep, exactly. Yeah. So it's sort of like here we say that, okay, we fix star to be all of the stars of the Sharknado movie, and then we can kind of join that with some other information. So we could ask here, maybe, you know, we could ask what types of things are they, which would not be very interesting. But we could ask for if we had more information for their dates of birth or whatever we would like. So here we fix it to be the stars of Sharknado, which would be John Hurd and Ed Ziering. And then we know here we have to fix somehow this to John Hurd, for example, and then we can join that with more information.
Okay.
Yeah, so it's like a join. So when we define it in the first line, then we fix it to be the stars of Sharknado, and then we can add some more data, right?
Okay, thank you.
No worries.
Yeah.
But to mention that the first line and the second line, we could actually swap these two lines and we would get the same solution. It's kind of like in joins in SQL or databases, we can reorder joins, we can swap the order in which they're done. We'll still get the same answer. So we could just start with movie stars star, which would get us all of the stars of any movie. And then we could find out, we could restrict that to be just the stars of the Sharknado movie.
Okay, thank you. Yeah.
Okay. So, but basic graph patterns. This here is referred to as a basic graph pattern, which is a set of triple patterns. And a good way to think of it is just as a graph. It's a graph like an RDF graph is, because we have triples. The one difference is that we can put variables in there. So if we think about it like that, then we see that actually our basic graph pattern, what's in our where clause here, is sort of like a graph, you know, like this. Okay, we have some variables which are new. And then what we're looking for is this mapping from this graph into this graph. How can we map these variables to nodes in the graph or to terms in the graph such that we get solutions, right? So this would be a mapping, specifically a homomorphism, but we map star to Ziering, movie to Sharknado. We see that somehow this graph matches the RDF graph. Okay, so that's a basic graph pattern. Here we refer to these as join variables, because essentially what we're doing here is almost the same as a join in an SQL setting. So here, these are called join variables, and these are variables appearing in more than one triple pattern. Well, actually, we could even have join variables in one triple pattern if we use the same variable twice, but okay. So what we're going to do is join these. We're only going, in each solution, they can only have one term, right? They can only be mapped to one thing. Okay, so what else do we have in SPARQL and SQL? We have a lot of features. Do we have similar such things in SPARQL? So for example, if we were to ask, what are the titles of the first two movies in the Sharknado series? What we're really asking for is, what is the title of Sharknado Union, right? What is the title of Sharknado 2, like Union in SQL? And we can write that. That's not a problem. So we can write this query here. So we say Sharknado series first movie, okay, Union Sharknado series second movie. Actually, okay, here. We don't know the IRIs here, right? So we need to query what is the first movie and what is the second movie. So we write it like this: get me the first movie, union, get me the second movie, and then join it with getting the titles. So we see that we can use some sort of relational algebra operators like union here to be able to express richer kinds of questions. And this will return as Sharknado, as being the name of Sharknado here, and Sharknado 2 being the name or title of Sharknado 2 here. So this union effectively takes the union of the solutions for this pattern here, which would be Sharknado, and the result solutions for this pattern here, the second one, which would be Sharknado 2. So now we have two solutions, and then we join each of them with the tile, and that gives us these solutions here. So this is similar to union in SQL. We can also do things like left joins, for example. So we can ask, for example, give me the titles of all movies, and if available, their first air date. So we're looking for information about movies. And some movies, we don't have their first aired date, right? So it means that we don't want to just drop the information about Sharknado 2 because it doesn't have the date. Rather, we'd like to leave it blank and still return the solution. And SPARQL offers us something called optional, which is like another name for left outer join, which means that we keep all of the solutions to the left, no matter what. And if possible, we extend them with the solutions from the right-hand side of the optional. So it says we're going to get all movies and their titles. Remember here, actually here we see that we can use some turtle syntax. So this is equivalent to movie movie or movie RDF type movie title, right? So we kind of have like two triples here. So we're getting the titles of things that are movies. And then we're saying optionally, if you have the first aired date available, please show it to me. If it's not available for that movie, return the movie anyways and leave the date to be blank. So here we see what the solutions will give us. So we have movie Sharknado, title Sharknado, and its date as it's available. In the case of Sharknado 2, there's no date available, so we get Sharknado 2, the title, and we get a blank here in the solutions for that. So, okay, so it's similar to left outer join in SQL, or just simply left join. Optional. So this here, in SQL, we refer to nulls, right? So the solutions can return nulls. In SPARQL, we rather call these unbounds. They are variables without a binding in a solution, effectively. And they can occur in for example, with optionals. They can also occur with unions in some cases and some other features. And it just essentially means that this variable it just has no binding. It's like as if in this one particular solution that the variable date isn't defined for that solution. Okay, what about if we wanted to do something like we wanted to filter based on the data? For example, we wanted to ask what movies were first aired in 2014. Well, we can start to use filters for that. We can use filters to do mainly conditions on, for example, on the terms on the terms that are used in the solutions. So what movies were first aired in 2014? Well, we need to express some sort of greater than, less than conditions here, right? So what we can do is write a query like this, where we get all of the movies and their first air dates. Okay, so this will return Sharknado, which is of type movie and has a first air date. And then it filters the dates to say that it must be greater than the 31st of December 2013. And it must be less than 31st of December 2014. So in terms of solutions, we get nothing, okay? Why do we get nothing? We see that actually there are no movies that were first aired in 2014. Okay, so we filter all the solutions and we see that the overall solutions are empty. So initially we have this solution here, but then the filter gets rid of it because this is not satisfying the condition. In particular, it's not greater than 31st of December 2013. Okay, so we get some empty results here. So we can use filter to be more precise about what kinds of solutions we want. And this is particularly useful for domains and ranges, but there's actually a whole bunch of different functions we can apply. So you might ask, first of all, what happens in this case if in the data, so here we're comparing date with an actual XSD date. And this we can do so we have some sort of ordering over dates. We have to be a little bit careful with time zones, but okay. So we can apply this sort of condition here. But what happens if we have an incompatible value in a solution? So a solution returns date mapped to a string, for example, that's not actually of type XSD date. So what happens in this case where we try to compare, maybe for example, we also try to compare a number with a string to see if they're equal or greater than, or whatever. So what happens in this case where we have an incompatible data type that we're comparing? Effectively, the filter will throw an error. So the filters can expect certain types, and they can also help to kind of map between different types. For example, they can still compare between integers and ints or longs or floats, numeric types. But in other cases, there's nothing you can really convert to. There's nothing, no sensible value to convert to. So the filters expect certain types to be satisfied, the operators and the functions. So if those types aren't satisfied, if we have something that's ill-defined or incompatible, then it throws an error, okay? And if it throws an error, this filter, what happens is rather than the whole query throwing an error, it just filters out one solution. So essentially an error, if for a solution we get an error, we just drop that solution and we continue to the next one. So it acts kind of like as if the filter were false simply, right? So it just filters the solution. So the filter conditions, they evaluate as true, false, or error. And only results evaluating as true are returned. So we can apply then over this sort of a logic of and or, right? So here we have our usual truth table. So we have A is true and B is true. Then we can do A or B is true, A and B is true, true, false, and so forth, right? So what happens in the case of error? If we have A is true and B is error, and we have A or B, what might we expect?
Error?
In this case, what it says is that the value of error shouldn't matter. So error is basically like, it could be true, it could be false, right?
Okay.
So what it does here is if there's true, yeah, exactly. Yeah. So this would be true, and the true and error here, this would be error, right? So because A and B, we really need to know the value of both. So in this case, this would be A and B would be error. And likewise, if we continue down and complete the table, we see that we have these values here. So we get true because we already have A is true, and that's sort of sufficient for A or B. And here it's true because B is true. These are errors because we would need to know both values to be sure of the results. So we give error and so forth. So false and error. Well, in this case, if B were true, then this would be true. So it depends on what the value of B is. So we say it's an error. Okay, and then A and B must be false, right? Because if A is false, it's enough to conclude that. This is the same, just the symmetric case. And then finally, error or error is error and error is error. Okay, so we have some operators, but we also have to consider what happens when we have false. We can also apply not. So not is not error is also error. Which is perhaps a big difference actually with false. So, okay. Of all the operators, I'm not going to go into them in a huge amount of detail, but these are here on the slides for reference. So we have some basic comparators or comparisons that we can do. So first of all, okay, we have not, we have or, and, equals, not equals, and then we have equals and not equals for specific types. So here means comparable. These are essentially certain types that we can compare. These would be things like numbers, booleans, strings, and so forth. There are things that we can't compare, like blank notes. We can't write, is this blank note equal to this other blank note, because the labels of blank notes don't matter, but most things we can compare. So we have equals, not equals, and so forth, less than, greater than. Then we have plus and minus, the unary positive and negative to say if a number is positive or negative. And then we have sum, subtraction, multiplication, division in this case here. So, okay, we have other functions to see things like existence, equality. We can check if a variable has some solution. If you remember the optional first air date, and we had a solution that just didn't have a value, like a null almost in SQL. This can check for these sorts of situations. We have conditionals, we have a coalesce, which will basically, given a bunch of terms or a bunch of filters, it will return the first one that's not an error or unbound. So it will return the first in the list that returns an RDF term rather than having something that's unbound or throwing an error. So this is useful if we want to maybe have multiple alternatives. We prefer maybe, let's say, the name in English versus the name in French versus the name in Spanish, but we'll take the Spanish name or the French name if it's available. What we can do is do optional for the label in English, optional for the label in Spanish, optional for the label in French, and then select in terms of the preference order we prefer, select the first one that's unbound. So we can say, give me the English label if it's unbound, otherwise give me the Spanish label if it's unbound, otherwise give me the French label if it's unbound, for example. So it's useful for specifying preference many times, or for trying different alternatives. Not exists allows us to filter basically queries where there's no solutions for a subquery, similar to SQL. Exists is the negation of that. Most people, exist is kind of a little bit useless. Most people will use not exist because exist is kind of like just doing a join with the subquery. Same term. This allows to make sure that two terms are really the same, which is slightly different from equals, because if we do, for example, 2.0 decimal equal to 2 integer, the equals will interpret the value and will say that's true. 2.0 is the same as 2. This here, same term, will not. It will actually check the very syntax of the RDF term. Is it the exact same IRI? Does it have the exact same string? So same term is used if we really want to see, is this exactly the same literal or IRI? We can check as a term in a list of terms, and we can check as a term not in a list of terms, which is sort of like shortcuts for equality with and, or shortcuts for equality with negation and, or negation and or, as you wish to express it. So next we have terms. We can check to see, for example, is a term an IRI, a blank note, a literal, a numeric value. We can get the string of a data type. We can get the language data. We can get the data type IRI, like I said, XSD integer, XSD int. We can create an IRI. We can create a fresh blank node. We can get the data type of, or we can create a new literal based on a string and a data type that we give, or a string and a language tag that we give. We can create a fresh IRI from a special scheme, a URN scheme, which is a universal resource names. Or we can create a fresh string based on that as well. So essentially there's ways, many of these things that, for example, these two functions are not that widely used, but we can have certain functions to check the type of a term, of an RDF term, and to create new RDF terms if we need those. We also have pretty typical functions for strings. Get the length of the strings, substring, uppercase, lowercase, starts, ends, before, after. We can encode for an IRI, so we can do a percent encoding of IRIs. We can concatenate two strings, check if the language matches of a literal. We can do a regex, a regular expression, to find strings or to ensure a string matches a regular expression. We can do replacements, so we can do some sort of string manipulation as well. In terms of numerics, we already saw the operators multiply, divide, add, and subtract. We also have absolute numbers, round numbers up or down, ceiling, take the ceiling of a number, the floor of a number, so round up or round down, and take a random number between 0 and 1 inclusive. And we have temporal functions. So we can get the current date time, we can get the year of a date, the month, the day of a date, the hours of the date, the minutes, the seconds. So we can extract all of the elements of a date or a date time. So we can get whatever elements we like from that date time. We can also get the current date. If we'd like to compare it, or maybe subtract two dates or subtract at least the years of two dates to see how many years ago it was, for example. We have some hashing functions where if we wanted to, maybe we have a database where we have some sensitive information, and rather than return that, we want to use some cryptographic, well, some of these are cryptographic hashes at least. We can take the hash of a string using some standard hashing functions to return that. So maybe I'll continue for 3. I know. Okay, so yeah, we're at the break time. Any questions? Or I know I went through these quickly, but it's sort of like just to give you a flavor of what kinds of operators and functions are there. And like going through all of them in detail is not really essential, but we'll be using a couple of these in the labs for sure. The most common ones are probably these operators here, your typical less than, equals, or, and, but oftentimes you might also use, for example, some of the string functions, for example, are useful, or some of the numerics. So as a general flavor, any questions or thoughts about that? Okay. So we can take a break. I'm slightly over the half hour until, well, it's almost 11 o'clock. So we can take a break until 11. Any questions or doubts?
I have a question.
Yep, go ahead. Yep.
Does SPARQL have any advantage over normal SQL?
It's a very good question. Yeah, it's a very good question. So first of all, it allows you to query RDF data. And RDF data essentially is more flexible than relational databases. Like we spoke about the kind of benefit of graphs, that you don't need to define a relational schema at the start. You don't need to do your UML or your diagram and think about what are all the tables and what are all the columns, but rather you can just start adding nodes and edges to your graph in a more flexible way. So in that sense, SPARQL allows you to query RDF data, and RDF data has these sorts of inherent advantages over relational databases. The other advantage that RDF has that we still have yet to see is that it uses web identifiers. So the idea will be that you can click on those and it will bring you to another page somewhere else on the web that describes that in more detail. So a lot in the labs we've been using the example namespace, which is just kind of a bit painful, but in reality, soon we're going to get there where those are going to be clickable things that we can click and it will transport us to a document elsewhere. So it means that actually RDF documents, the things we described there, they can be referenced from across the web. So I can point to a specific element of an RDF graph and say, you know, I can point to that from across the web and I can extend the description or do whatever, or refer to someone to that. So SPARQL in that sense is allows you to query RDF, and the RDF graph model has some advantages over relational databases. The second thing would be that there are specific features in SPARQL that allow you to create graphs, which are quite cool. Like, for example, you can create paths in graphs that match a certain regular expression. And we'll see that in the next class. And those things are much more difficult and much less intuitive to express in SQL. You can express them with recursive SQL, but they're not so clear. Yeah.
Thank you.
Yep, and that's not to say that this is better than SQL, right? SQL has other advantages clearly, but you know, there's certain cases where it's a good idea to use, or it might be a better idea to use RDF. Cool. Any other questions or doubts? Okay, so we'll take a break until 11. I'll see if I can find the post active. I'll post it in a second. Okay, see you in a few minutes. Okay. So as mentioned before, there's certain types that might be compatible, and we can also do some in certain cases, casting between different types. So, okay, we can cast from every term to itself. So this is the from, string, float, double, decimal, int, data type, Boolean, IRI, or literal. And these are the things we can sometimes cast to. Where green or Y means yes, we can cast. M means maybe. So in certain cases, we can do that. And N means no, never. So we can always cast from something to itself, right? Where's this called? Oh, no, I'm not sure why this isn't. Okay, yeah, so we have IRIs or literals. Okay, so we can cast IRIs and literals to strings. We can't cast anything to IRIs or literals, although we could use a function to create an IRI or a literal. So we can pretty much cast anything to a string, which just basically gets its lexical value. So, okay, in the case of string, for example, we see lots of maybes. So we can maybe cast a string to a data type, and that just depends on whether or not the string is in the format of a data type, whether it would be a lexically valid data type, which is year, dash, month, dash, day, for example. So so we see that we can have some casting between different. I won't go through the entire table, but we can cast in certain cases to different data types, and we can always cast things to strings to get their string value. So an IRI, for example, if we cast it to a string, it just basically means we get a string that has the IRI rather than an IRI type. So let's take a slightly more complex example that uses some of the functions that we've seen previously, namely relating to strings. So before we saw this, we're combining certain elements of queries that we had seen before, which is that we're going to take the union of the first movie and the second movie. So we're going to take Sharknado and Sharknado 2, and then we're going to optionally ask for the first date if available, which will return the state in the case of Sharknado and a blank or unbound in the case of Sharknado 2. And then we're going to get the titles of those movies, okay? Sharknado and Sharknado 2 here based on title. And finally, we're going to filter the movies based on this expression here. And what this says is we're going to apply a regular expression to match the title. And we're only going to return results that match the regular expression. So we take the string of the title. So we just extract a simple string here. So we get something that's of type string rather than a full literal with its language. So in this case, we return Sharknado, and in this case, we return Sharknado 2, the second one. And then we apply this regex here, which asks for some prefix. And then we have one character that's in the range of 0 to 9, so a number, and then some suffix, right? So essentially, we're asking for titles that have a number in them. So that would be Sharknado 2. So the solutions for this, we would expect Sharknado 2 to be the only one returned, as it's the only one with a number in its title. We leave the date blank because it doesn't have one, but we express that as an optional. And that gives us the solution. So the filter here, we apply a regular expression on the title to select certain solutions, or to filter certain solutions and keep other ones. Another example with the where clause is we can express negation of a sort. So what does this mean? It means that we can, using a certain trick, we can check to see, for example, movies without first aired dates. So how does this work? We return a movie, we get all movies, and then we optionally find the date if available. And then we use this filter expression, which is not bound, which says that it only returns the solutions where the date is not defined, where there's no solution for the date or where the date is an unbound. So what solutions does this return? This would return us the movies where the date would be unbound. In this case, it would be Sharknado 2. So we can use optional combined with filter not bound to express assertive negation in a roundabout way. In SPARQL 1.1, we can more directly express this sort of thing with not exists or minus. There's various features for that. But here we have a trick to do it purely in the original SPARQL version. So we have Sharknado 2, and since this is blank, we return it as it's not bound. So we can do a sort of negation as well if we like. Okay, we've seen the where clause for SPARQL 1.0. There's more things that we'll be able to express in SPARQL 1.1, but we'll talk about them in the next class. So in terms of the query types, here we're talking about the select star. Okay, so select star is probably the most intuitive. It's sort of like SQL that returns as a table of results, right? So select star just basically tells us that we're going to return all of the solutions that we find. We're going to return all of the variables for each solution. So all of the variables here will appear in our table of results. So we have movie and star. What happens if we're only interested in one of the variables or a subset of the variables? In that case, we can use, for example, select star, and this will return as only the solutions for that variable. An interesting thing here is that we have duplicate solutions. So we see inserting appears twice. And this is because by default, SPARQL will apply bag semantics. So it means that we can return duplicates, much like in SQL. If we wanted to get rid of those, as you might guess, how we might want to get rid of those. So, okay, by default, we apply what's called this bag semantics. So the number of results must correspond to the number of matches in the data. And we get inserting twice because inserting is involved in one solution here and another solution here, right? So since he appears in two different solutions, he's returned twice here. If we wanted to remove duplicates, we can apply the distinct keyword, same as in SQL. And this will just return the inserting once. So we get rid of all the duplicate solutions for the variables that are returned. Okay. So each result must be unique. Each result row here, each row in the results table must be unique in this case. There is another option, which is not in SQL, as far as I know, at least. The SQL standard has like 3,000 pages, so it's a bit hard to say what's definitely in there, what's definitely not in there. But if we have select reduced star, what this allows us, it basically tells the engine that we don't care. We don't care if there are duplicates or not. We just want solutions. And this allows the SPARQL engine to do whatever is most efficient. If it thinks it's more efficient to get rid of duplicates, maybe to avoid lots of intermediate data when we're doing joins and so forth, then it can apply that. But if it thinks that there's more of a cost to actually getting rid of the duplicates, it can just return all of the duplicates. So it allows the engine to choose whether or not it returns duplicates. So and it can return duplicates sometimes and not in other cases. So it can return any sort of set of solutions between bag and set semantics. So here we have two options. It creates this sort of non-determinism that both of these are valid solutions for this query. Select reduced. So we may, but we do not need to return duplicates, and it allows the engine to do what is most efficient. We have a completely different type of query here, which is ask. And what ask says is basically return true or false. It says return true if there is some solution for the query, and return false otherwise. So ask basically is like, it's like asking, is there a movie that has some star? And since we have a solution, we return true in this case. Okay. So it's a sort of a Boolean query. Is there a solution for this? Is there something that matches the where pattern in the data? So it returns true if there is a match or false otherwise. We have a third type of query, which is something you also won't see in SQL, which is construct. So in the case of SQL, you run queries over tables and you get back tables as results. In the case of SPARQL Select, you run queries over graphs and you get back tables as result. So what about the idea of running queries over graphs and getting graphs as results? So how SPARQL does this is it allows you to define a second basic graph pattern. It could be the same one, but it allows you to define a construct basic graph pattern, which basically gives you a template for constructing a graph, an RDF graph based on the solutions. So what happens is that for every solution returned from the where that matches the where, we're going to replace the elements of the construct according to those solutions. So basically it says that for every star of a movie, we're going to create a new triple, which is the result for the star, job, actor. So we're going to say that every star of a movie has the job actor. And in this case, it will match the where clause, and then it will return these results here. And then we'll take the star of each result, which will be John Hurd in Zering, and we'll replace it here. And this will create two unique triples in RDF, right? So we can use construct to specify a way to run a query over an RDF graph and get an RDF graph as a result. So this returns an RDF graph based on the matching construct clause. Okay, and one last type. So we have 4 types in total, and the 4th is describe. And this is a non-normative feature, which means that it's included in the standard, but what exactly is returned is up to the engine, up to the implementation. So the standard defines the syntax for these queries, but doesn't tell you exactly what it should return. So the describe basically says, describe the elements here, right? So it also returns like construct, it will return an RDF graph. And what describe returns, it says, give me RDF data about every result here. So essentially we take the union of the descriptions for every result. So the stars here again are Sharknado, are John Hurd and Zering. And what we're going to do is return for each of them an RDF graph that describes that result. So it can be what is their type, what is their label, maybe all of the triples where John Hurd appears, maybe as an object or as a subject or both. Whatever in particular is returned by the SPARQL engine is up to that SPARQL engine. So it could just be all of the triples in the RDF graph that involve that term. So, and then we just take the union of those graphs for every solution as the result. So it's basically return me an RDF graph describing all of the solutions for star. And whatever is returned specifically is up to the RDF engine. So whatever is returned is left open to the implementation. Okay, any questions or doubts? So we have 4 types: select, which is very like SQL, ask, the Boolean version, construct, where we can create custom RDF graphs from our solutions, and describe, which is basically giving an RDF graph describing some elements of the solutions, some description in RDF of each of the solutions. Solution modifiers is the next features. Again, very familiar from SQL. We can order results, ascending or descending. We can also order lexicographically on multiple items. So we can order by age, then by location, and so forth. We can apply a limit to return only the first n results, and we can, or return only n results, I should say. And we can use offset to skip the first n results. So we can get we can skip maybe the first 10 results in terms of first air date, and then return from result 11 to 20, right? So that would be offset 10, limit 10, right? So we skip 10 results and then we return 10 more, similar to SQL. So how might we ask for the second and third most recently released movies? What we can do is we can skip the first one and then return 2 more results, okay? Which would be a query like this. So order by descending, where we get the movies in descending order of with the newest movies at the start. Then we offset 1, we skip 1 result, and we return the next 2. The ordering here of offset and limit doesn't really matter, right? So we're always going to apply offset first and then limit afterwards. So this says skip 1 result and then return the next 2. So we were getting the second and third most recently released movies. Okay, so these are solution modifiers. It's worth noting that without order by, the results for limits with for queries with limit or offset might be non-deterministic. So if we don't specify here this order by, it's basically any solution that returns two results, assuming there are at least two movies with dates in the RDF graph. Any solutions with two movies is valid, right? Because we never specified the order. So we can select any two movies and that would be valid. There's no default ordering or anything like that. So basically the solutions under any ordering would be valid. So this creates again some sort of non-determinism because we have all of the different options of all the different orderings if we don't explicitly state the order that we wish to use. So again, to mention that the order of execution is always order into offset into limit. So changing the order of limit and offset makes no difference to the query solutions. So if you write offset then limit or limit then offset, it doesn't matter. Okay, so these queries here are equivalent. This notation means that they're equivalent. So limit 2, offset 1, limit 2. I actually don't think that you can change the order of order by. I think you can for some reason syntactically write these queries, but it doesn't allow you to say limit 2 order by offset. No, I'm not 100% certain of that. In any case, the order of execution is always order into offset into limit for the solution modifiers. Yeah, so order by must come before limit or offset according to the query syntax. So okay, it's a little bit weird maybe that they allow you to reorder these two specific solution modifiers, but okay. It's maybe to simplify the grammar. Any questions about solution modifiers? They're very similar to SQL, so there are things they're probably pretty straightforward. The last part of SPARQL 1.0 that we need to look at is named graphs. Named graphs is kind of tricky. So we'll have a look at it and see. So first of all, there's a formal definition here. The core idea is that in SPARQL, we're not going to just be able to query one RDF graph. Like in SQL, we don't just query one table, right? But rather we can query a collection of RDF graphs. So what we can do is we can have different graphs in our SPARQL engine, different RDF graphs, and we name each graph. Okay, so we might have 5 graphs and we give each of those 5 graphs a different name. So that allows us then to query over specific graphs when we want to. The other thing is that we can have a graph without any name, which is sort of like the default graph, which is the graph that we'll query or do inserts to if we don't provide any name. So that's the core idea, and this is formalized as a data set. Okay, so a data set consists of G, a graph, and then a list of named graph pairs. So each pair here is an RDF graph. So this is an RDF graph called the default graph. And this here is a pair, which is an RDF graph and a name for that RDF graph. So we have one default graph and we have K named graphs here. And each named graph is essentially a pair of a name and a graph. So what are the names? The names are IRIs. So we can name different graphs with IRIs, and then we can select which of them we want to query or to do inserts or updates to based on what we want to do. So all of these are RDF graphs. We have pairwise distinct IRIs, which means we can only use each name once. G is called a default graph, which we refer to if we never mention a graph in our update or query. And after that, each of these pairs G, N, each pair of graph and name is a name graph. Okay. So we have this data set here, and the idea is this will enable us to query a selection of different graphs, or to select which graphs we want to query, rather than just having one massive graph. So the core idea again is that you can use SPARQL to support multiple RDF graphs. So you can do queries or inserts or updates to different graphs. It allows you to separate, for example, the RDF graphs that come from different sources. It allows you maybe to more easily update the one particular graph, right? It allows you to select that you only want results from particular graphs, And so it has various use cases, but it essentially allows you to separate data into different graphs rather than just having to always work with one big graph that's the union of all the graphs you have. So an example data set would be this, where we split the data rather than having one big graph. We split the data into a default graph, which in this case, it's used, for example, for listing all of the movies of the Sharknado series. Then we have a graph for Sharknado called Sharknado TTL, okay, Sharknado Turtle. Maybe it's a document that we uploaded, which just describes the Sharknado movie. And then we have a second name graph, which just describes the Sharknado 2 movie. So essentially here we have two named graphs and a default graph. Right. So if we have a data set in our SPARQL engine, in our SPARQL index, then in a query, we can pick what's called an active data set from the named graphs. So we can select some of these graphs that we would like to query to form a new data set, D prime, which we're just going to use for that query. So it essentially allows us to select what graphs we want to query on. We can create this active data set using two features. We can use from, and we can use from named. So the from is used to define the default graph. It's used to define this graph here for the query specific data set that we're going to use. If multiple graphs are specified, they are RDF merged. So we can essentially take multiple of these graphs, G1 to GK. We can take 2 of them, 5 of them, 7 of them, merge them all into a default graph. And if we specify multiple, then we'll RDF merge them. Okay, what does RDF merge mean? We'll come back. I'll explain that in a second. So it's essentially the union where we keep the blank nodes distinguished. So we basically take the union of the graph and make sure that their blank nodes are kept distinct. Second feature is from named, and this allows us to define what named graphs we're going to have in our query specific data set. So it's used to specify the active named graphs to be used for the query. So using either feature clears the index data set. So once we use from or from named, we're going to clear everything. So then we add things explicitly back to the data set. So we're going to see some examples of this to try to illustrate. The first thing is to remember what is an RDF merge, which is what from uses. An RDF merge is essentially this idea that if we have two different RDF graphs that happen to have the same blank nodes, we don't want to end up with a situation where we merge these, right? We want to avoid this sort of situation because the blank nodes here are local identifiers and they're really distinct. So we want to keep them separate. So we don't do it this way, but rather what we'll do is we'll somehow rewrite the blank nodes in whatever way we like to make sure that in the union, they're not going to be, there's not going to be conflicts or clashes between these blank nodes. So here we'll just rewrite this to B1, G1, B2, G2, and here B1, G2, B2, G2. And now we see in our resulting RDF graph, when we take the union after making the blank nodes distinct, we don't have these clashes anymore. So this means that this is called an RDF merge, which is essentially a union, but we're careful to rename the blank nodes and make sure that the blank nodes of both sides are distinct so we can rename them. And renaming blank nodes doesn't really matter because the labels of blank nodes is not important. They're like local strings. So that's the RDF merge. It's this fancy union of graphs. So when we're creating a data set for a query, we have our index data set, which is what we've actually stored in our SPARQL engine. And then we have a query data set, which is basically if we don't specify from or from named, it will just be the indexed data set without any changes. So this will be what our query is going to run over. If there is a sum from or from named feature, then if we have from, for example, N1 and N2, then we're going to take here the RDF merge, as we just saw, of G1 and G2, which will be our default graph. And then if we have from named N3 and N4, then we're going to keep as named graphs N3 and N4, where we keep the names, right? So we see that this is still a data set where we have one default graph here, the merge of G1 and G2, And now we have two named graphs, G3 and G4 and 3 and F4. Okay, so this is the main idea. So with this, we can construct query-specific data sets to run our queries on. Another example, we can just use from, and in that case, our default, our query data set will just be the merge of G1 and G2. We could also use only from named, in which case we would have an empty default graph, and we would just have some named graphs then. Okay, so we can then query specific parts of the data set, either whatever the data set is for the query, using graph. And graph allows us to specify either the URI or this should probably say IRI now, of a named graph over which the pattern is evaluated. So this can also be a variable that ranges over all the named graphs. So we can query over all the named graphs at once. However, if we use the graph feature, it does not access the default graph. It's only over named graphs. So if we want to query the default graph, we don't use graph. We don't use this feature. If we do, we can use graph to access a named graph. Okay, so that's a lot of details. What's left are solution or examples, but I'm run out of time. So I've explained all of the details of how from named and graph works. These are all the features we have, and what's left is to show you some examples that will go through that, and it should help to clarify how these features combine and what sorts of results they return. Any questions or doubts? As you can see, we're almost done, but I think we can leave it for Monday or for Wednesday. Okay, if there's no questions, we'll have our first lab on Wednesday on SPARQL. The other thing I wanted to mention is the reading groups. We can start to think about forming the groups for the reading groups. So the idea will be that you'll find, you select a research paper of interest to you. I'll provide some tips on how to find research papers, which ones are acceptable, which ones aren't. You'll be forming a group of 3. Within your group, you can select a paper, and then you'll be asked to upload a short video that provides a summary of the paper. And then there will be a peer review. So essentially, you'll review some of the presentations of other groups. And the core idea is not just that you read maybe some research, but also that together with all of the talks, we get a sort of an overview of the types of research that's ongoing in this area. So this is a very active research area. And as part of the kind of postgrad element of the course, it's sort of nice to be able to see what sorts of research is going, what types of research are going on. So I'll post more, we'll coordinate that by the forum mainly. So next week, I think Monday is feriado, if I'm not mistaken. So, or is it the week after? I think it's next week. So we can maybe use that week, whichever week Monday is feriado. I'll put more details in the forum, but we can dedicate a little bit of time to the reading groups as well. If there are any questions or doubts? Okay, so we'll finish the class on Wednesday. We'll have the first lab then. So see you on Wednesday.
Thank you. Bye-bye.
Bye.
Bye.
Bye.